Hi everyone, this is the second video on the series on implicit regularization, Benign interpolation, and Benign overparametrisation. So today we will talk about Benign interpolation and we will focus on the intuition. So we will not do clean proof of result, and instead we'll try to get some intuition and try to understand what's going on. So we start again with our linear model, Gaussian linear model. So I'll remind you, so we have some observation, yi, which is the scalar product of some xi that we observe also with some beta stars that we don't know. And these observations are corrupted by some noise, epsilon i's, which are IID standard Gaussian, sigma 2. So we denote by capital X the matrix where we split x1 to xn by rho. And as we have done in the previous video, we will minimize the squares by gradient descent. And what we have seen in the last video is that in this case, what we will select is an estimator which is given by x plus y. And we want to understand how this estimator behaves when we are in a high-dimensional interpolating regime. So let us start with a few computations in order to understand what's going on. So let us take some x in Rp, and let us try to predict the value y for this x. So the prediction will be with beta hat scalar x, where beta hat is given by this. So can write it. And by using the fact that y is equal to x beta star plus epsilon, here what I will have is this decomposition here. So I will have x plus x beta star and x plus epsilon, and it will be scalar x. And what is x plus x? This is exactly equal to the projection on the range of x transpose. So why is it so? Because if you look at x, so if you take the SED of x, it is the sum over k of sigma k, uk, vk transpose. And if you take x plus, it will be the sum over k, 1 over sigma k, vk, uk transpose. So you see that if you take the product of the two matrices, you will end up with simply x plus x that will be equal to the sum over k. So you will have sigma k over sigma k, so this will be equal to 1. And then what will be the vector? You will have vk, vk transpose. Okay, so this cancels to 1. So at the end, you obtain simply something which corresponds to the projection on the image of x transpose, on the range of x transpose. All right, so now all the following, so we denote by px transpose, the projection on the range of x transpose. And I can write this as beta star plus the identity minus the projection. So I have this decomposition here, where first I have the target, so this is what I would like to use in order to do my prediction. And then I have two additional terms. So I have a first term here that does not depend on epsilon, and which corresponds to a bias. And this bias is equal to, so you have x scalar beta star minus its projection on the range of x transpose. And then you have a third term, and this third term corresponds to the noise term, so it depends on epsilon. So it is epsilon scalar x. So here you have x scalar x plus epsilon, so you can take x plus on the other side. So you have x scalar epsilon times x transpose plus x. So this will be a Gaussian distribution because you take a linear transform of epsilon, which is a Gaussian vector. And what you will have is that this is a real random variable which has a variance which is equal to the norm of this vector. And the norm of this vector is equal to this quantity here. So conditionally on the design capital X, you have that this term follows a Gaussian reduction, a Gaussian distribution with this variance. All right, so maybe let me discuss a little bit this formula. So the main point is that what you can observe is that if you take some x here, so the x where you try to evaluate something, which is orthogonal to the range of x transpose, which is the same as the range of x plus, then you will simply predict by 0. Why? Because this belongs to the range of x plus, this is orthogonal to x plus, so these two terms will be orthogonal in this case. This is why you will predict by 0. So if you predict by 0, it means that you will have a large bias, but you won't have any variance. Okay? 0 has no variance. So you see that in the orthogonal of the range of x transpose, you just predict by 0, so no variance at all, but a large bias. Now, let you think to a case where you are in a very high dimensional setting. So assume that the rank of x, so it is equal to n, so x is full rank, but n is much smaller than p. So in this case, the projection on the range of x transpose of x, so x transpose has the same rank than x, so it will be also equal to n, then the projection will have a norm that will be much smaller in general than the norm of x. For some standard x, so for example, thanks to some x that is sampled according to some Gaussian distribution where the covariance sigma is equal to the identity up to constant, which means that the spectrum of lambda, of sigma, sorry, is bounded away from 0 and bounded away from above. So what you can see is that for such an x, only a small part of x will be used for the prediction, okay? Because in your scalar product, you only have the part which is in the projection, and this will be very small in norms compared to this. So you will have something that will be very small. So we try to make all this more specific, and below we'll discuss two cases, which will be the case where sigma is equal to the identity. This is the isotropic case. And then we'll consider the spike model, where you have a low dimensional part with a lot of signal, and you have a high dimensional part with a very low signal, so with rho very small compared to 1. And we will discuss these two cases, and in the next video, we will analyze the general case. So, before moving to these two cases, let us evaluate the average prediction error of the estimator. So I remind you that our estimator is given by x plus y, and I use the fact here that y is equal to x beta star plus epsilon. So I have beta hat, which is equal to the projection on the range of x transpose of beta star plus x plus epsilon. So if I want to look at the prediction error conditionally on the design x, what I will do, I will compare the prediction beta hat scalar x to the prediction beta star scalar x. I take the difference to the square, and then I will take expectation. Okay? So this corresponds to the average prediction error conditionally on the design x. So I take this expectation, where x follows the Gaussian distribution n0 sigma, okay, al the xi, and epsilon is a Gaussian vector with covariance sigma 2 identity. So just because I think it is nicer to write it like this, so here my expectation is only over x on epsilon, so I will denote this conditional expectation like this, where this means that I take expectation with respect to small x and with respect to epsilon. So let me use this decomposition here in this formula. All right, this is what I do here. So what I have, I have beta star, which comes from here, and I have the projection on x transpose of beta star, which comes from here, right? And the additional term is x plus epsilon scalar x. And I remind you what we have seen in the last lecture is that you have the decomposition Rp is equal to the kernel of x in orthogonal sum with the range of x transpose. So by doing this decomposition, I have that the identity minus the projection is equal to the projection on the kernel of x. Right? So I can simplify this by the projection on the kernel of x. All right, so now I have a square. So what I will do, as usual, I will expand the square. So if I expand the square, I will have the square of this term. It gives me this term. And you can see that this term does not depend on epsilon, so I just have expectation with respect to small x. And I will have the square of this term. And if you look at the square of this term, so as we have seen, this term here follows Gaussian distribution with a variance which is equal to the norm of x plus transpose applied to x. Okay? So if I take the expectation of the square of this quantity here, so this is all this quantity that follows this distribution, I will have simply the variance, so I will simply have this term, and this is what I have here. Finally, I have an additional term, which is the cross term. So if I take the cross term, so the product of these two terms multiplied by 2, I will have an expectation that will be equal to 0, essentially because I have something that will be linear in epsilon. And since epsilon is centered and everything is independent, I will have that these cross terms are equal to 0. So it can be convenient to rewrite this term as follows. So here, what I have is a scalar product of x with x plus transpose x. Okay, so I can rewrite it by taking my x here and move it on the other side. So I will have x transpose x plus transpose. And x plus transpose, you can check that it is equal to x transpose x plus, okay? So when I take my expectation, what I will have the expectation, so this term does not depend on small x, so my expectation will be only on this term. So since I have something linear, the expectation of this term will give me sigma, and this term will give me this term, all right? So you see that this term, which is a variance term, is exactly equal to sigma 2, sigma times the Moore-Penrose pseudo-inverse of x transpose x. And here I use the Frobenius scalar product. So this is just the classical Euclidean scalar product for matrices. And now if I look at this first term, so again this term is linear in x transpose. So when I will take the expectation of x transpose, I will have sigma. So I end up with a bias which is given by this formula. All right, so here we have a general formula for our Gaussian setting for the risk, where we have two terms. We have this bias and we have this variance. And we try to understand how they behave in some simple cases. And the first case that we will investigate is the isotropic case, where the covariance is equal to identity. So all my data is generated by Gaussian distribution, which has identity as a covariance. Okay, so I just write it plainly here. So I have my linear model, and here the noise is Gaussian, but also the covariates are Gaussian. So in order to understand this term, I need to understand how this term behaves, right? And to understand how this term behaves, what I need is to understand the SVD of x. So let's look at the SVD of x. Right, so I take my x, I take the SVD of x, and I mean, this is not a proof, but this is a simple remark, and with this simple remark, you can understand what are the order of magnitude. So if you take the Frobenius norm to the square of x, so you can write what it is. So the Frobenius norm is just the L2 norm and the entries. So it is equal to the sum over ij of the xij square. So taking the expectation, what you will have is that since xij is n01, you will have that this sum, so you have I which goes from 1 to n and j that goes from 1 to p, is equal to n times p. So this is one way to write the Frobenius norm, but you know also that the Frobenius norm is equal to the sum of the singular value to the square. So it is also the expectation of the sum of the singular value to the square. So you have n non-zero singular values, because you know that x is n times p, with p much larger than n. Okay, so we are in a setting where p is much larger than n. So the rank of x will be equal to the minimum of the two, which is n. Okay, so you know that you have only n non-zero singular values, and the singular value, so you can always upper bound each singular value by the largest singular value. So you see that it is always smaller than n times the largest singular value. In particular, if you compare these two numbers, you see that the largest singular value to the square in expectation is larger than p. So this suggests that your singular value should scale like square root p when p is large compared to n. And this is actually what occurs. So for example, there is a nice result of Davidson and Sarek that we will not prove, that tells us that in our Gaussian setting, if I look at the expectation of the singular value, they are between square root p plus square root n and square root p minus square root n. And actually, if you take all these singular values here, and you do an histogram of this singular value, you will end up with an histogram which will have in this shape when p and n goes to infinity with p larger than n. Okay, so you have all your singular values that will be minus square root p minus n and square root p plus square root n, at least in expectation. So what you know is that this is a result in expectation, but this is also something which is one Lipschitz with respect to the Frobenius norm, since the Frobenius norm is the sum over k of sigma k to the square. So since it is one Lipschitz, you can apply Gaussian concentration inequality. So you know that this quantity will be very concentrated around its norm, its mean, sorry. So when p is very large compared to n, okay, so this is essentially square root p, this is essentially square root p, you only have Gaussian fluctuation, so you will have that essentially, as a first approximation, your singular value will behave like square root p. All right. So here, this is not a proof of this result. If you want to see a proof of this result, or not using Davidson and Sarek, but a direct proof, you can look at proposition 12.9 in the lecture notes, where you have a full proof of this result in a non-asymptotic setting. All right, so let's take for granted this result, and what does it mean at the end that we have this? So I remind you that if I look at, so I have x, which is the sum over k of sigma hat k uk vk transpose. So x transpose x is equal to the sum over k of sigma hat k to the square vk transpose. Okay. But what we have seen is that this is essentially equal to P. So essentially what we have is that X transpose X is equal to P times the sum over K of the VK transpose. And this term is nothing but the projection on the range of X transpose. So what we have seen is that when P is large compared to N, as a first approximation, we can think of X transpose X as being equal to P times the projection on X transpose. And this is something that you will use in order to try to understand what is the variance of our predictor. So what we have seen a few slides ago is that the average prediction error is given by this formula. And now we want to apply the fact that we are in the case where sigma is equal to the identity. Okay, so when sigma is equal to the identity, this cancels out. So I will just have the square norm of the projection of beta star on the kernel of X. And here, so I will have the identity. So if I take the scalar product with the identity, I just take the trace. So the variance terms will simply be sigma 2 times the trace of X transpose X plus. Okay, and I remind you that we have seen that X transpose X is essentially P times the projection over X transpose. So let us use this. So sigma 2 is the trace of X transpose X plus, the variance is equal to sigma 2 times this trace. And what I will have is sigma 2 times the sum of 1 over sigma hat K for K going from 1 to N. This is because I take the Moore-Penrose pseudo inverse. And this term is essentially equal to 1 over P. So what I have is essentially N times 1 over P. So my variance, when P is large and with high probability with respect to the design X, will be essentially be equal to sigma 2 N over P. And this is very striking because usually we are used to have sigma 2 the dimension divided by N. But here what you see is that you have sigma 2 N divided by the dimension. So this is very unusual. And in particular, if P goes to infinity, so P much larger than N, you will have that this quantity goes to 0. Okay? So for very large inputs, your variance goes to 0. And this must be related to the fact that when P is very large, you will have that this is much smaller than this. I will discuss a little bit more this later. Right, so what you see is that in the interpolation regime, when you take the gradient least square, you will have almost no variance. So of course here we did some informal computation. So I refer to the next video for a proof of this result, and actually for more general setting. So let me discuss a little bit this result. So here we have considered a risk which is integrated with respect to small x. So let me take a given x, okay, let's say with a norm equal to p. So if I take the variance only with respect to epsilon, so I consider small x as being fixed. So this is exactly the computation that we have done before. It is equal to sigma 2 x transpose x plus x. Okay, so that is what we have seen just before. If you take this term, the variance is given by this quantity. All right, so it's equal to this quantity, and what we have seen is that this quantity, so just recall the formula, is essentially sigma 2, so 1 over p, sorry, so sigma 2 is in factor, so this quantity is essentially 1 over p times the projection on X transpose. So here I will have sigma 2 over p times the square norm of the projection of x transpose of x to the square. So now let us look at two different situations. Okay, if I have an x which is in the range of x transpose, okay, so this is in the range of my xi, where the xi are the learning data set, then the projection will be equal to x, so the variance will be equal to sigma 2 times the square norm of x divided by p. Okay, and since I have the square norm of x equal to p, here I have something of order sigma 2. So what you can see is that on the space spanned by the xi, you have a strong overfit. Okay, you have a variance which is like sigma 2, so it does not go to 0 with n or with p or with nothing. So the first message is that as long as you are in the linear span, which is spanned by your data point, so by the xi, which is simply the range of x transpose, you will have a strong overfit of your predictor. But what happens is that in our case where x has the same distribution of the xi, so it is a Gaussian distribution, so here with covariance equal to identity, you will have that with high probability, the projection on x transpose of x will have a norm which will be much, much smaller than the norm of x squared, right? And this is due to the fact that in your high-dimensional space, when you take a new input, this new input will be essentially not correlated with your initial input x1, xn that you have used for learning. Okay, so a new x is almost not correlating with the learning data point x1, xn, which are the column of x. And for this reason, when you look at the variance, so the variance, I remind you, is equal to this term, this variance will be small. So to summarize what we have discussed is that we overfit on a small space, which is the space spanned by learning input, but we underfit everywhere else. And for this reason, we will have a large bias on a small variance when p is large compared to n. All right, so far we have only discussed a variance term, so for given x or integrated with respect to x here. Let us look now at the bias. So if I look at the bias, so I remind you that we have seen that the bias is equal to the square norm of the projection on the kernel of x of beta star. So I use again this decomposition here in order to say that this projection is equal to the identity minus the projection on the range of x transpose. And by using Pythagore, this square norm is equal to the square norm of beta star minus the square norm of beta star projected on the range of x transpose. So this does not depend on the design, and the question is, how does it behave? So what is the situation? Here, I remind you, so each xi is standard Gaussian in RP. So we are completely isotropic. So if you look at the range of X transpose, so you know that it is a space of dimension n. And typically, this range will be uniformly distributed over all the space of dimension n. Okay, there is no direction that is preferred because everything is invariant by rotation because everything is isotropic. Sigma is equal to the identity. So the range of x can take any direction among all the possible subspace of dimension n. So if you look, so think, for example, in expectation, it means that you will take only a fraction n over p of the norm of your vector. Okay, so if you look at the square norm of the projection on x transpose of beta to the square, when p is large, this will behave like n over p times the square norm of beta. So you see that you will only get a small fraction, the fraction n over p, of the norm of your input. So you will have something at the end that with large probability with respect to the design will be like the square norm times 1 minus n over p. So the 1 comes from here, and the n over p comes from here. So you see that when p becomes very large, this goes to 0, and you have something which is as large as the square norm of beta star. Okay? So this is essentially due to the fact that when p is very large, you will estimate with 0, your prediction will be 0, so you will just have the norm of beta star as a bias, and you will have 0 variance. So to summarize this isotropic case, when sigma is equal to the identity, what we have is that the risk is equal to the norm of beta star plus n over p sigma 2 minus the norm of beta star. And what you see is that when p is large compared to n, this term will be small, so you will essentially have this term, which is large. So what you can see is that in this setting, we will not have a good prediction risk, but the problem will not come from the variance, but from the bias. So this is completely orthogonal to our initial intuition, where we had in mind that if you are in very high dimension, we will have a lot of variance, but a very flexible model, so not a large bias. But here this is the contrary. We will have a large bias, but a variance which is almost 0. All right, so now let us move to a bit more complex case where we will be anisotropic, and we'll consider what we usually call the spike model, where sigma can be decomposed as a sum of two terms. So first, on the first part in sigma, I will have, so I have 0 everywhere here. I will have the identity on a small subspace of dimension k. Okay? And then, on the orthogonal, I will have the identity but multiplied by some rho which is very small. Okay? So this corresponds to the signal level, and this signal level on this part will be very small. And I will assume that k, this term, is very small compared to n, and n is very small compared to p. And again, rho is very small compared to 1. So here what you can see is the case where the covariance is essentially low rank with a high signal plus a small perturbation, but which is spread on all the space. All right, so now we want to understand how behave x transpose x plus, as I remind you that if you look at the variance term, which is here, the variance term, Vx, is the scalar product of sigma with x transpose x plus. So we need to understand this term. So again, let us do a small reasoning, okay? So if I look at 1 over n x transpose x, so this is the empirical covariance in our case, okay? And if you look at the empirical covariance, so here you have something which is low dimensional. So you can imagine that when k is small compared to n, you will be able to estimate very well this part of the covariance. Okay, so here you have sigma hat. So you imagine that sigma hat will give you a good estimation of the low dimensional part. And this is actually what will occur. So if you look at the empirical covariance, on this space, you will essentially have the identity. And then you have an additional term. And what can you say about this additional term? So you know that the rank of x, so it is the minimum of n and p, so it is equal to n, since n is smaller than p. So you know that this has a rank which is equal to n. So since this has rank k, because this corresponds to this term, you know that here you will have something of rank n minus k. And let's try to figure out what is this part of the empirical covariance. So we know that it has a rank which is n minus k. And what we have also is that here, this is completely isotropic, okay? So here we have something which is isotropic with respect to this part of the space. So exactly as before, we can expect that all the singular value will be almost the same. So this part here should be equal to something, let's say lambda, times the projection on a space of dimension n minus k, right? And the only question is to understand what is this proportional factor. So to understand what is this proportional factor, what you will do is to look at the trace of sigma. So if I look at the trace of sigma, what do I have? So here I have k, which corresponds to this k term here, and here I have rho multiplied by p minus k. But I remind you that this is sigma hat, okay? So we can expect that this is also essentially equal to the trace of sigma hat, which is nothing but the trace of what we are computing 1 over n x transpose x. So if this is true, then the scalar product, the scalar factor that we had, lambda, must be such that here, this quantity times n minus k, because this is dimension that I have, must be equal to this term. So it means that my lambda must be equal to this term divided by n minus k. So this is why my lambda must be equal to this term. So what we have understood is that my empirical covariance should be essentially equal to the identity on this space, because it is low dimensional with a lot of signal. And on the orthogonal, it should essentially be some projection on some space of dimension n minus k with a factor which should be equal to this term, just because the trace of sigma hat must be essentially equal to this term. All right, so let us take this formula for granted. And this is essentially true. So if I take this formula, so now I can multiply everything by n. So I will have x transpose x. So x transpose x, I will have n times the identity. And then I will multiply this by n. But I have in mind that k is small compared to n and p. So if k is small compared to n and p, I can forget about the k here. And when I multiply by n, this will cancel out. So what will remain is only rho times p. So what I will have is n times the identity, rho times p, times this random projection. Okay? So this is an approximation for x transpose x. And now if I want to have the Moore-Penrose pseudo-inverse, so I just keep in mind the fact that here, this belongs to this space here, and this is a projection which is in this space, right? So these two are orthogonal. So when I will take the Moore-Penrose pseudo-inverse, I will take the Moore-Penrose pseudo-inverse of this guy and this guy. So we will have 1 over n identity plus 1 over rho p, this random projection. So at the end, again, I will assume that this formula is correct. What do I have for the variance? So my variance is sigma 2 my matrix times sigma. So I have to take the scalar product between this matrix here and this one. But I remind you that this and this is orthogonal, this and this is orthogonal. So when I take the scalar product, so first I will have the scalar product between these two terms. So this will be the norm of the identity divided by n. So I will have k for the square norm of the identity divided by n. Now, if I look at the scalar product of this term with this term, since this space belongs to this part here, I will have that this and this is orthogonal. So I will have that the scalar product between these two terms is equal, of these two terms here is equal to 0. So this will cancel out. Now, if I look at the scalar product of this term and this term for the same reason, because they are orthogonal, this will cancel out. So the last term that will be non-zero will be this term. So you can see that the row cancel out. So I just have sigma 2 over p as a factor, and I have the Frobenius scalar product, so the Frobenius is missing here, between this term and this term. So what do I have? So here I have the identity on this region of the space, and here I have a projector of dimension n minus k. So I will just have the trace of this projector, and the trace of the projector is equal to the dimension of the space, which is n minus k. And for k small compared to n, we can think to it as being essentially equal to n. So at the end, if this is essentially equal to n, here I will have n over p sigma 2. So I obtain this formula for the variance. So here you can see something interesting. For the low dimensional part, we have something where we have a lot of signal, we have something like k over n. And this is what we are used to. We are used to have the dimension divided by the sample size, right? And this is exactly the classical setting on the recover head. But then there is this additional term, which corresponds to the high dimensional part with low signal. And this low dimensional term, exactly as before, it will be like n over p, at least when k is small compared to n compared to p. And this is exactly the same phenomenon as we have seen before, and this is small due to the high dimension of the input. So what you can see is that here, at least in terms of variance, you will have a variance that will essentially correspond to the variance of the low dimensional part. And for the high dimensional part, this will be killed and this will goes to 0 when p goes to the infinity. So again, you see that you have a regularization effect of the high dimension, which is due to the fact that gradient descent selects some specific solution, and this solution has a minimal norm. All right, so that's all for this video. So we have only seen some computations that are informal. What we will do in the next video, so first we will consider a general covariance, and we will do a rigorous analysis, and we will prove a sharp upper bound on this variance, and in particular we will recover the results of today. So our informal results were not too stupid. So see you soon for the next video.